This is Project 26090, Naphtha Reforming. Our team members are Lamar, Leonel, Elazar, and Andrew. We are all chemical engineering students. Every gallon of gasoline we use today is the result of complex engineering processes designed to meet strict performance and regulatory standards. However, many refineries still produce streams like naphtha that are underutilized and do not meet modern fuel requirements. Our project was to upgrade this stream into useful products like hydrogen-rich gas, liquid petroleum gas, and methaformate.
Our project is framed around a real-world refinery challenge where we act as a consulting team hired to upgrade an existing oil refinery facility in Texas City, Texas. The refinery lacks sufficient upgrading capacity to meet modern fuel quality and market demands. In particular, there is a growing need for higher octane gasoline blending components as well as an increased production of lighter and more valuable products like liquid petroleum gas. Right now, the refinery's excess naphtha represents an underutilized opportunity. Pure naphtha has relatively low research octane number, or RON, which limits its direct use in gasoline blending. At the same time, stricter fuel regulations and consumer demand require gasoline with higher octane ratings, typically around 90 RON or higher. This creates a clear gap between the refinery's current capabilities and what the market actually demands. RON measures a fuel's capability to resist knocking or premature detonation under lower stress engine conditions. A higher RON means the fuel is more stable under pressure, allowing higher performance engines to run smoothly without damage. You may recognize RON from the numbers you press when filling your car's tank at the gas station. To address this, our team was tasked with designing and integrating a methaforming unit into the existing refinery. The goal of this unit is to convert naphtha into higher value products, specifically hydrogen-rich gas, or HRG, liquefied petroleum gas, LPG, and methaformate, while achieving a target RON of 90.
Now I'm going to walk through the overall process and highlight the major unit operations in our methaforming system, what each one does, and why it was selected. We begin with the feed preparation section, where full-range naphtha and ethanol are first combined in an inline mixer. This ensures a uniform composition before entering the system. The mixture then flows into a surge tank, which helps dampen any flow fluctuations and provides steady operation to downstream equipment. From there, a centrifugal pump pressurizes the stream up to the reactor operating conditions. Next, the feed enters a two-stage heat exchanger train, which is a key design choice in our system. The first heat exchanger begins preheating the feed using available thermal energy from the byproducts of our reactor, improving the overall energy efficiency of our system. We specifically chose to use two heat exchangers before the reactor to maximize heat integration and reduce the duty required by the fire heater. Instead of relying entirely on external fuel, we gradually raise the temperature in stages, which lowers operating costs and improves thermal efficiency. This is especially important in refinery systems where energy consumption is a major economic driver. After preheating the stream enters the fired heater, which brings the mixture up to the required reactor inlet temperature of about 350 degrees Celsius and forces a phase change. This ensures the feed has sufficient energy to drive the methaforming reactions.
The core of the methaforming process is a zinc zeolite-based catalytic packed bed reactor. In this unit, the naphtha and ethanol undergo a series of reactions including dehydrogenation, isomerization, and alkylation. These reactions increase the octane number of the product while generating valuable byproducts such as hydrogen-rich gas and LPG. This unit is critical because it is where the actual upgrading of low-value naphtha into high-value gasoline blend stock occurs. Once the reaction is complete, the hot reactor effluent is sent to a cooling heat exchanger. This step reduces the temperature of the stream to conditions suitable for phase separation. Cooling is necessary because separation efficiency in downstream units depend heavily on temperature. The cooled stream then enters a three-phase separator. This unit separates the mixture based on phase behavior. The hydrogen-rich gas exits as a vapor stream, while the liquids are separated into water and hydrocarbons. The reason we use a three-phase separator is to efficiently isolate the hydrogen-rich gas early on in the process, which is important because hydrogen is a valuable utility to offset the fuel gas needed in the fired heater.
The liquid stream is pumped to the distillation column, specifically a stabilizing column. This column separates light components from heavier ones. The overhead, which is LPG, consists of components like propane and butane. The bottom products from the column is the methaformate, which is our main product stream. This stream has high octane number and is suitable for blending into gasoline. To support the column, we include several auxiliary units: a partial condenser, which condenses parts of the overhead vapor, a reflux drum, which separates vapors and liquids, a reflux pump, which sends liquids back to improve separation efficiency, and the reboiler, which provides heat to drive the separation. Overall, this process was designed to follow a logical progression: feed conditioning, controlled heating, catalytic reaction, phase separation, and finally product purification. So far, we walked through the physical process, how naphtha and ethanol move through each unit op and are ultimately converted into high-value products. But designing the flow alone isn't enough. To make sure the system actually works in a real-world refining setting, we need to validate it through detailed process simulation and accurate component modeling. One of the biggest challenges we faced was how to represent complex refining streams like naphtha and methaformate. Initially, we were modeling as pseudocomponents based on a boiling point curve, which was useful for early design, but not fully captures the important properties like phase behaviors or octane rating. To improve accuracy, we transitioned to a real component model using weighted sum average with MATLAB. We assigned specific weights to each chemical species of a list of 130 that could possibly exist in naphtha. We included key parameters such as boiling point, hydrocarbon family, and densities. This allowed us to more realistically simulate how the mixture behaves throughout the process. We then performed a series of validation checks to ensure our model was theoretically accurate based on literature. This included matching the boiling point curves, verifying the composition trends, and most importantly, calculating the research octane number using corrected blending method. From this, we found that our final product achieved an RON about 90, meeting our design targets, while the feed naphtha remained in a realistic range. In addition, our system consumed roughly 27,000 kilograms per hour of naphtha, producing our products of methaformate, LPG, and HRG. So overall, this simulation step confirms that the process we designed is not only theoretically sound, but also capable of meeting realistic performance and product specifications.
The sales ended up being $174 million per year. The HRG produced will be used as a utility for energy recovery of the fuel gas. Speaking of utility and energy consumption, there are 4 main utilities used for this plant: steam, cooling water, electricity, and fuel gas. These utilities were modeled using Aspen. Using the values from Aspen, the utility cost annually is $600,000. Overall, our plant is profitable. With a capital investment of $51 million, our sales exceed our costs, yielding a 10.58% return on investment over a 5-year payback period. With a total plant life of 10 years, these economic values are completely reasonable and make this plant a likely option for many refineries.
Next, we're going to be talking about our preliminary piping and instrumentation diagram. Starting with feed preparation and heating, our goal is to deliver a steady, properly conditioned stream to the reactor. The surge tanks help dampen flow fluctuations, while the feed pump ensures a consistent flow rate. We use the heat exchanger to recover energy from the process and preheat the feed before it enters the fired heater. The fired heater is one of the most critical pieces of equipment, so it is controlled with a temperature control loop to ensure the correct reactor inlet temperature. For safety, we include a fail-close shutdown valve on the fuel gas line, which automatically isolates fuel in the event of overheating. In the reactor section, we focus on maintaining safe and effective reaction conditions. The reactor is monitored through temperature and pressure instrumentation, since these directly impact conversion and safety. A cooling jacket on the reactor prevents overheating in the case of a runaway reactor. After the reactor, the effluent is cooled and sent to a flash drum for phase separation. Level control in the flash drum is especially important to prevent liquid carryover into the gas stream or starving the downstream stabilization column of feed. In the final section, we focus on product separation and quality. The stabilizer column uses temperature and pressure control to separate LPG from the heavier methaformate product. The partial condenser controls the overhead temperature, while the reflux drum and pump recycle liquid back into the column to improve separation efficiency. The reboiler provides heat input at the bottom of the column, which is controlled to maintain consistent product composition.
Overall, we were successful in designing a naphtha reforming unit that processes 5,000 barrels per stream day of naphtha into liquid petroleum gas, hydrogen-rich gas, and RON 90 methaformate.
We would like to acknowledge and thank our professor, Dr. Adriana Brush, and our professional mentor, Fred Brinker, for their support and guidance throughout the year.
Thank you for watching our video.
And we're excited to see you guys for Senior Design Day.
Reformers out.
Why do you